LCMS because it's so finicky.
Yeah, I mean, I like the LCMS though, just because like I don't like the fragmentation, because it's like, is this actually, like I get a mass and it's like, is this actually my product mass or is this just a fragment,
Yeah, it's hard to
it's
tell.
less ambiguous.
That's cool.
Hi, sorry, I was trying to log in through my computer, but it wouldn't let me, so I was like, okay, I guess I gotta go to my phone now. But let's see. Hello, everyone. I don't know, did you already introduce yourself?
No, I've just been chatting with Professor Stanford. My name is Cole. I'm a second year grad student at University of Chicago, specializing in organic chemistry and organometallic chemistry. So I do have some, actually, I have kind of a slide for background stuff, so I'll just go into that. Sorry.
Yeah, if you want, you can go right ahead.
Can everyone see my screen?
Yeah.
Okay, and feel free to just jump in with questions if you have any at any point in this. So I'm like I said, I'm a second year grad student at University of Chicago. I work for Professor Guangbin Dong. Our group specializes in transition metal catalysis with an emphasis towards like applications for synthesis. So mainly we do CH bond activation with like palladium and iridium catalysis, as well as CC activation through rhodium catalysis, as well as some kind of more new stuff in our group with using boron for pretty precise editing for molecules. I don't have anything. I don't work on that area. I don't have anything in my presentation about it, but it is very interesting. So if you're interested in learning more, I would definitely check our group's website for some of our recent papers on that. So a little bit about me. So I am from Mount Prospect originally. I went to Harper College from 2015 to 2017, where I took OChem with Professor Stanford. I'd say that was when I really started getting into chemistry, was that class, and with his guidance and his mentorship and suggestions, I applied for a summer research internship at Hope College in Holland, Michigan, just across the lake. So I did that for 10 weeks in the summer after my second year at Harper. And then in the following fall, I had transferred into UIC, just downtown. And then I joined another lab there and was there for 3 years. And then, but also in my first summer after UIC, I went back to Hope. So I very much enjoyed it there. Definitely highly recommend it for research if any of you are interested in that, and in particular for chemistry. And then I graduated in 2020, and then in the fall 2020, I started in the PhD program in the chem department at University of Chicago. So like I said, I work in organic and organometallic chemistry. So for those of you who aren't really familiar with organometallic chemistry, so just wanted to include a little bit of background to help with this talk. Bonding and reactions for organometallic complexes are quite a bit different than for like organic molecules that the way we teach it in OChem. So in OChem, all bonds are pretty much just S and P orbitals, but now with transition metals, you have these d orbitals, which kind of allow for a lot of more complex and more more potentially interesting modes of bonding. You can have interactions from the metal to a single atom, or to an orbital, molecular orbital between two atoms, like in an alkene. So you can have the alkene donating electrons to an empty this is the right way, but from filled pi orbital in the alkene to an empty metal d orbital, and conversely, you can have filled metal d orbitals donating to empty antibonding orbitals in alkenes. So this kind of allows for some different modes of bonding and reactivity that you may have otherwise seen. So as far as mechanistic steps go, so some kind of common ones for organometallics that are relevant to this talk are oxidative addition. It's pretty much just a metal can insert itself right between two atoms and just break into a bond. So this is normally used to start off catalytic cycles. And then the opposite is reductive elimination, which just puts them back together and reduces the metal. These are just kind of in equilibrium with each other. And then another step, so like I said, you can have these kind of weird bonding patterns between like metals and alkenes. So when you have it bonded like that, an alkene can just kind of insert into a metal hydrogen or a metal carbon bond through a process called migratory insertion. And then there's a reverse process called beta hydride elimination or beta carbon elimination that just regenerates the coordinated alkene. So in my group, I've been working in CC activation, catalyzed with rhodium. So for some background with that, back in the 90s, it was discovered that rhodium-1 complexes can undergo oxidative addition into carbon-carbon bonds. And normally for oxidative addition, especially for palladium catalysis, it'll kind of be involved with, typically what we view as more reactive bonds like carbon halogen, as opposed to inert, both thermodynamically and kinetically stable CC bonds. So this is able to happen. So the metal carbon bonds that form are relatively weak compared to that carbon-carbon bond, but because you're relieving ring strain, that kind of is a driving force for this. So once you have this metallic cycle where rhodium's kind of inserted into it, you can then get some new and interesting reactions that can alter carbon frameworks, which is typically pretty challenging to do otherwise. So it's then shown, you can have the carbonyl group deinsert to give cyclopropanes, as well as, if you hydrogenate it, you can just get the ring opening and then further hydrogenation to get an alcohol. So a big breakthrough with this type of chemistry was in the early 2000s. Masahiro Murakami over in Japan, their group has been active in this area, and they showed that through this CC activation, through oxidative addition, you can have a tethered alkene undergo migratory insertion to give this ring expanded bicyclic product. So this goes by this general mechanism, so which we call cut and sew. The rhodium basically just cuts into a bond through oxidative addition. The ligand, in this case, this alkene, can coordinate to it and then undergo migratory insertion, and then reductive elimination frees the rhodium to go back and do it again with another molecule. So through this type of process, you can basically just insert things into carbon-carbon bonds, which by typical OChem retrosynthetic disconnections is not really something that we really think of. So this gives a really neat way to build up carbon frameworks. So our group has done a lot of work in this. All these examples, except for this ketone one, are from our group. So we've shown that using either these benzocyclobutenones or cyclobutenones with a tethered pi system, we can build these pretty complex frameworks with pretty good efficiency and relatively quickly. And if we use a chiral ligand, we can get really high enantioselectivity in a lot of cases for these. So this has worked with alkenes, alkynes, amines, ketones, and all these shown here are intramolecular. We do have a couple intermolecular examples using ethylene and alkynes and styrenes. So then as you can see, you can really quickly build up some complex frameworks. So we've applied this in our group to multiple total syntheses. So in all these, the key step for building the core of the natural product is achieved through this cut and sew reaction. So one thing we've wanted to do going forward based on all this is to expand the scope of what pie systems can work in this reaction. So we've looked at, so I've been working with trying to get cut and sew to work for NN double bonds. So this could give us a way to introduce nitrogen into organic molecules through rhodium catalysis. Well, these types of bonds are kind of less likely to be encountered. They are nevertheless found in a lot of natural products and drug molecules, particularly some pretty high-selling ones. So finding new ways to add NN bonds into organic molecules is definitely of interest. And a longer term goal with this type of work is that if we can get cut and sew with NN double bonds to work, we can kind of use that as a proof of concept for some much more ambitious things, namely trying to take inert nitrogen, and there's many conditions reported for activation of nitrogen, nitrogen gas, and then find a way to use that as a pie system for our cut and sew reaction. So normally, if you have any organic molecules with nitrogen, typically the workflow for getting to that is starting with steam reformation of methane to form hydrogen gas, and then using hydrogen gas plus N2 through the Haber-Bosch process to form ammonia. This is super efficient, but it does, requires very harsh conditions, high temperature, high pressure, and typically when it's run on very, very large industrial scales that require a lot of infrastructure to take place. And then through various other downstream transformations, this ammonia is ultimately incorporated into organic molecules. So we were wondering, in the long term, can we use our cut and sew chemistry to, just go directly from N2 to nitrogen-containing compounds? So we started off trying to do an intermolecular reaction with these azodicarboxylates. Unfortunately, we only found reduction of these potentially with the hydride coming from either the alkyl groups on the azodicarboxylate or from solvent, but no desired product was found. And we found that increasing the temperature, we can start to see very small amount of this decarbonylation product. So this is a good indication that CC activation is happening, because for the decarbonylation to happen, you have to have the rhodium do the oxidative addition, then deinsert the carbonyl group from the ketone, and then reductive elimination to form the three-membered ring. So at this point, we switched from azodicarboxylates to these diazines with these really brightly colored compounds with where the substituents on the nitrogen are these phenyl groups. So initially we screened some ligands and different catalysts, and we found that with this DTBM segphos, which is a very electron-rich ligand that donates a lot of electrons to the metal and makes oxidative addition a lot more facile. We've had a lot of success in previous CC reactions with this. So with that, we found 46% of some new product, and then it took a while to conclusively identify. But after using this brominated derivative, and then we were able to, carrying out the reaction with that, we were able to grow a crystal and analyze by X-ray diffraction to, conclusively assign this structure to it. So this is very, very different than what we were anticipating, which kind of raised a lot of questions about what's going on here. But nevertheless, these benzimidazoles are pretty prevalent in bioactive molecules, in particular, a lot of top-selling drugs. So and also these annulated benzimidazoles with this ring, this extra ring connected to it. There aren't that many methods for making these. So this offers a pretty simple way to make these from relatively simple starting materials. So looking into the literature, we found that if you treat azobenzene with various transition metal complexes, you get this orthosemidine complex through a rearrangement. This is reported for various transition metals at high temperatures. So looking further, we found that with ruthenium, it's also been reported that benzimetazoles like this can be synthesized, presumably by oxidizing either an amine or alcohol and then reacting with the orthosemidine complex. Though these require pretty harsh conditions as well as CO atmosphere, which is not ideal to be using. Very hazardous. So we also found that it's reported that rhodium can form these orthosemidine complexes with azobenzene at pretty high temperatures. So we assume that this could be operative in our reaction. And then as a control experiment, we use this amine that kind of resembles it. And we were actually able to still get the product when that replaced azobenzene. So based on that, we proposed this mechanism. So the conversion from the azobenzene to the rhodium orthosemidine, we're not super sure on the mechanism. This transformation is reported for a lot of metals, but nobody's really done any mechanism studies into it. So I can't really say with great confidence that this is what's happening, but we are pretty confident that it's going from this starting material to this product by some way. So from there, we propose that this can do a nucleophilic attack on the carbonyl. Proton transfer can give this complex, which can then do a beta oxygen elimination to give this rhodium hydroxide complex. That can do another 1,2 addition to the amine with this nucleophilic nitrogen to give this. And so this is a pre-aromatic complex. And we propose that this is where the CC activation occurs. So this carbon-carbon bond can be broken to form this alkyl rhodium complex. And this would be driven by both aromatization and the stabilization gain from that, as well as by relieving the high ring strain in this four-membered ring. So from there, we propose that a CH activation with a concerted deprotonation by the hydroxide can release water and then also form this this metallocycle. And then beta carbon elimination could potentially give this complex, which can undergo reinsertion, basically just to kind of move things around a little bit. And then reductive elimination can give our product. So this is kind of in line with some other reported reactions where rhodium aryl species can add to cyclobutanones and then undergo beta carbon elimination for opening four-membered rings. So there's some precedence to support this. So then going forward, we worked on optimizing the reaction, just screening different catalysts and ligands. We found that increasing the loading of rhodium actually hinders the reaction, so we kept it at 5 mol%. And then looking at solvent, we found that dioxane, which we had been using, was still optimal, so we kept that as it was. And then looking at a variety of phosphine ligands, we found that BINAP, relatively simple ligand, performs the best, giving us a 52% yield of the product. So then we looked at if we can get an anti-selectivity in this by screening a bunch of different bidentate phosphine ligands, which would create a chiral environment for the rhodium to react in and favor one enantiomer over the other. Unfortunately, we saw no enantiomer selectivity. We just got a racemic mix of product in pretty much all cases. So this kind of led us to revise our mechanism for what could be happening, since if the rhodium is acting as we had proposed it was, if it has a chiral ligand on it, it should definitely be giving us at least some enantiomer selectivity. So we proposed that it may not be a kind of strictly organometallic mechanism, but rather a radical one, which would explain the lack of enantiomer selectivity. So we kept the same proposal up until this pre-aromatic intermediate. And then from there, where things would differ is that instead of beta carbon elimination, you have a homolytic cleavage of this CC bond to form this radical, which, and then also, giving forming a bond here and then giving an electron to rhodium to form rhodium-2. So this would give a pretty unstable radical, but this could also be kind of balanced by aromatization here, as well as opening up a strained ring. And then this can undergo this phenyl migration and then to form this more stable radical. And then this radical can couple with this aryl group to then give this radical intermediate, which can undergo elimination by rhodium to give the product and regenerate the catalyst. So we do have some basis for a lot of these single electron transfer steps. So a couple years ago, our group reported another strategy for CC activation through being driven by aromatization. So we showed that we can take a carbonyl or a ketone here and then basically just remove the ketone through the strategy, the CC activation strategy, where first we form this this hydrazone, and then that can do a 3+2 cycle addition with 1,3-butadiene that can isomerize, and then this is a pre-aromatic complex intermediate, which can then undergo some reactions with iridium. So iridium can oxidatively add into this NH bond, and then that can do a similar transformation to what we proposed, where there's just a single electron transfer to form this, aromatize this, and then break a CC bond to get this radical, and this radical can then recombine with the iridium to get iridium-3, and then just do a traditional reductive elimination step to get the product. Also, this should be ethyl, not methyl. So we proposed something similar could be happening here. And then we also had shown for the phenyl group coupling with the radical, using the same strategy. If this is taking place on a ketone with an aryl group tethered to it, it can cyclize presumably through this similar mechanism where it forms this resonance stabilized radical, which can then undergo a hydrogen elimination to re-aromatize and free up the catalyst to keep reacting. So with this in mind, we also tried iridium that had been used in those previous methods, and we found that it does work, though not as effectively as rhodium. That's kind of where things were at with this project. And then obviously this definitely took a turn that we weren't expecting as far as the cut and sew stuff went. So we then kind of went back to the drawing board with it. And as you saw before, a lot of the cut and sew stuff we've reported is intramolecular reactions, just because that, having everything tied together always simplifies stuff and keeps things running more smoothly. So with that in mind, we thought, what if we could use a substrate like this for a cut and sew reaction, as well as this would also address the kind of problem I mentioned before, where we don't have many cut and sew methods for making heterocycles. So this would add into that. And, if we can have NN double bonds working for cut and sew, we can kind of start thinking more about NN triple bonds. So then with that in mind, I developed the synthesis for a substrate for this. So starting from this commercially available ketone, you can do a Wittig reaction to get this alkene. And then under these conditions here, so with this acid chloride with zinc, you can form ketene, which is highly reactive and can do a 2+2 cycle addition with the alkene to get. So initially you'll get this product, but with a chlorine here and a chlorine here, and then just treatment with more zinc. We'll just, through a radical mechanism, and with acid, we'll just, kind of rip it off. It's pretty harsh and not really fun to do. It's very, very, very messy and kind of a pain to work up, but, it's pretty reliable. So then protecting this will give, this intermediate, and then using palladium catalysis for Buchwald-Hartwig amination, you can form a CN bond where the with the aryl bromide using this protected phenylhydrazine. And then if we use tetrabutammonium fluoride, we can selectively deprotect the Bach group while leaving this acid-sensitive group still there. And then that can be removed on its own after to finally get this product or this substrate, which we can use for our cut and sew reaction. As we started this, one of the concerns was if this could also do that azobenzene rearrangement, but fortunately we found before that this requires pretty high temperature, and if we lower it any further than about like 130, we don't get any we don't get any conversion of this azobenzene. So we figured that just by lowering the temperature, we should be able to avoid that. So we started off looking for, what's the lowest temperature we can run this at while still getting some conversion. So it turns out, around 110 degrees was the sweet spot for it. That's where we started seeing the decarbonylation product, which is indicative of, the rhodium CC oxidative addition taking place. So that stuff wasn't a problem. So it seemed like the migratory insertion was where we were running into issues. So my advisor suggested trying Lewis acids to help promote the migratory insertion. So we did that, screened several Lewis acids, and found that we could get some new product, which had, we saw full conversion of this, but then we saw the product with the same mass through mass spec. So it was a good sign, though the NMR didn't really match up with what we were expecting. So we thought maybe it could be this, but then after growing a crystal, we got another X-ray structure and once again found something that we were definitely not expecting. So we get this tricyclic compound as a single diastereomer. And while this was unexpected, it's arguably more interesting as a structure to be forming as opposed to what we were originally going for, as this can, parts of this can be found in some cytotoxic natural products like these communism alkaloids, and as well as some other natural products. So going forward, then we propose this mechanism where we have two catalytic cycles going on. So first is just the typical cut and sew process where you get the rhodium breaking into the CC bond for the cut and sew mechanism, and then NN bond undergoing migratory insertion, then reductive elimination to release the rhodium and then release this product. And then we propose that rhodium can then oxidatively add into the NN single bond to get this, which can then undergo beta hydride elimination to give this amine, and then the amine can then undergo migratory insertion into the rhodium hydride bond to give this, followed by reductive elimination to give the product. So things were looking good. We were pretty happy at first and thought we had gotten at least not the product we had expected, but presumably through the same initially through the same mechanism we were going for. However, then we did some control experiments, and we actually found that even without rhodium, we could still see very decreased yield with just zinc triflate, as the Lewis acid. So somehow that is able to mediate this transformation on its own, though much less effectively. So this led us to reconsider the mechanism, which at this point, just a disclaimer, we don't really have any data to back it up. So this is kind of just conjecture, but you have to have some mechanism consistent with just zinc being the active component in this. So we proposed that zinc can coordinate to the carbonyl and make it, the carbonyl-carbon molar electrophilic, which can then be attacked by the lone pair on this nitrogen. And then this carbonyl can reform and then break this CC bond to relieve the ring strain, and then reform the CC bond reform the CN bond to get what we originally wanted as our product. And then this could somehow, with the Lewis acid coordinating to it, this could somehow mediate either heterolytic or homolytic cleavage of the NN bond, followed by an elimination of this hydrogen to give an amine, and then Lewis acid coordination to the amine, making it more electrophilic and then susceptible to intramolecular addition of the NH bond across it. So we're still not really sure on this, but this is one possibility we suggested. So we continued optimization with just rhodium, just because it seems including the rhodium as well as the Lewis acid, just because it seems to make it run much more smoothly for whatever reason. Screening some Lewis acids, we found that zinc triflate still is superior, especially compared to other zinc salts. And then looking at some other metal triflates and other pretty strong Lewis acids, we still found that zinc triflate was ideal, as well as compared to some Bronsted acids. Then we found that just by lowering the temperature, we can get a pretty significant increase in yield, up to 52%. And then by switching the solvent to acetonitrile, we can get a much higher yield. We also found that at this lower temperature, the zinc by itself doesn't actually seem to cause the reaction to take place. So mechanistically, there's still a lot of stuff to hash out with this and figure out, but optimization is going decently well so far. So we tried to expand the scope of this to a shorter tether, because if presumably this could then give us these types of scaffolds, which can be found in a lot of natural products. So unfortunately, though, we didn't see any product with this substrate. So lastly, I want to talk about a project I just started about a week ago. Previously, a former group member had worked on this reaction. So previously, as I'd shown, all the cyclobutanones that we've used are, have a substituent here, which makes them achiral. In this case, when you have it on the alpha carbon, now you have a chiral center, so you have a mix of enantiomers, and it was found that using rhodium with a chiral ligand, even at room temperature, we can get the cut-and-sew reaction to take place. But more interestingly, we can only have one enantiomer undergoing the reaction. So this is a process called kinetic resolution. So basically what's going on is, so in normal reaction, both enantiomers will kind of react basically the same. There's no way to discriminate between the two. The reaction rate should be the same. But when you have this rhodium with this chiral ligand creating a chiral environment where the way it interacts with each enantiomer is different, you have the activation energy for, in this case, for reaction with the S isomer being, the activation energy is much lower, so the rate is a lot faster. When you add the rhodium with the chiral ligand to the mix of them, it will only react with, or it'll preferentially react with the S enantiomer and leave the R enantiomer unreacted. And then, at that point, you get the product. So that can control the stereochemistry at this carbon by only reacting with the S enantiomer. So with this in mind, I had proposed to my advisor if we could try something like this, where we have indole tethered to it, tethered to a cyclobutanone at the alpha carbon, which could potentially give, through kinetic resolution, and then the chiral ligand controlling the outcome of the stereochemistry of these two carbons as well, we can potentially get three contiguous stereocenters in one step. And then this could be applied for total synthesis. So this is like the core of strychnine, which uses a rat poison. So it's not particularly exciting, but if you look in the literature, many total synthesis groups over the years, it's kind of been a very common target for total synthesis, just due to the a lot of the features of it, especially the multiple stereocenters in it. So this isn't strychnine, but this is a related alkaloid. So I propose that if we can get this cut-and-sew and kinetic resolution reactant to work, we can get this, and then deprotecting this nitrogen and alkylating with this, we can get this intermediate, and then using palladium enolate chemistry, we can form this natural product. So this is only one synthesis has been published for this in 15 steps. So Presumably, if this can work, this would shorten it down to about half of that. And in addition to the kind of novelty of forming 3 of the 4 stereo centers in just one step. And then this can be prepared through from some commercially available starting materials. This one's commercially available. This can be made from something commercially available, though I almost started a sodium fire last week trying to make it, but I didn't, so it's all good. So like I said, I just recently started this, but I've got all the components made so far. I just got to react these to get the starting material. So that's what I've been working on. So that's all I had to present. I just wanted to thank you all for the opportunity to talk about my research. And want to thank my advisor, Guangbin, for all his guidance with all these projects, as well as Sophia, who's been an undergrad that I've been mentoring. She's been very helpful with the intramolecular diazine insertion project. I'd like to thank all my lab mates in the CC subgroup for all their helpful discussion, as well as my lab mates Daniel and Shinyoung for other helpful discussions, and my lab mate Shusuke for collecting my XRD data, and then all the Dawn group members for all their help and support. That's all I had. If you guys have any questions, I'd be happy to answer.
Which one are you most hopeful for?
I would say the total synthesis one. I feel a little biased towards that because like the other ones haven't really actually been cut and sew, as you've seen. Still is interesting, but not quite as in line with what our group is doing. But I think the total synthesis one would be cool if it works. So I'm keeping my fingers crossed for that one.
So I'm curious about how you started the sodium fire.
So I ran it at a small scale just because it was my first time using sodium as I use it for distilling solvent and stuff, but not as a reactant for reactions. And then I should have been working it up in the glove box. I figured because it was a small amount, it would be fine, and because most of it had been used in the reaction. So I was, the procedure was to, let it cool down and then filter it all and collect the filtrate with the product, wash with ether. And then as I was doing that, I felt the glass funnel I was filtering it through started to get very, very hot. So I, called the postdoc in the fume hood next to me for help. And he was just like, yeah, just throw it in this bin, douse it in hexane to quench it. And then, it was all good though. No fires. I got my product. So
double bonus. I was curious also with, you talked about the NN double bond insertions that you were doing. Can you, by analogy, do that with carbon nitrogen double bonds or carbon oxygen double bonds, or is that something that's already been done?
Yeah, so those are the only other examples for making heterocycles through cut and sew. We had so our group reported using CN double bonds for cut and sew, and then another group, we're in, I think, Switzerland, showed that ketones can do that as well. So to some extent, it kind of feels like the well is dry and we're scraping the bottom of the barrel with the NN double bond stuff. But if it works, it works. So
you can get a publication, right?
Yep.
I was wondering how much time are you then in the lab, and then are you guys as a group trying to figure out what you got? I'm not entirely sure about how that whole process goes.
So it depends. It'll vary lab to lab. So for my lab, my advisor is pretty hands off, which I definitely prefer. I'd rather not have somebody micromanaging everything I do. It's also good because there's not really a set hours. It's because we have subgroup meetings every week where we go over our progress from the previous week, and then get feedback from my professor and from other people in my lab. So that like, there's not really a time expectation, like you don't have to clock in at this time or that time, but as long as you're getting whatever you need done in the week, whatever it takes. Like, so for me, I am not a morning person, so I typically work pretty late, like till like midnight or something, but I don't get there till fairly late either. So I do like that about it. Some labs are some labs the PI has a bit more of a clear timetable expectation. But typically I would say I'm definitely there more like, so organic chemistry definitely is more time intensive in terms of how often you're in lab. I know some people in PChem who are there quite less frequently, but there are certain times depending on what they're doing that they're there for a lot more often because they have really specialized instruments they have to use, and only certain times they can use them. So sometimes for them are more busy than others. It's pretty consistent for me though. For OChem, I would say definitely more than 40 hours a week. Typically maybe closer to 60. Typically never more than that. Every now and then there's some weeks like that, but it's definitely more than a full-time job. But it's doable though.
I think she also was interested in understanding how much collaboration do you do with your lab mates?
Yeah, so everybody in my group has their own projects. So you do have a lot of ownership over what you're doing, but at the same time, like I said, my advisor's kind of hands off. So like he's there to help if you need help, but a lot of it's like collaborative. If it's like, hey, I've never done this technique before, I can ask one of my lab mates to show me how to do it. Or, I'm unsure about this NMR spectrum. Can you help me like clarify it? So everybody has their own projects, but it is pretty collaborative, I would say, in terms of like, people helping each other out. But, at the end of the day, I'd say there's a lot of independence expected.
Thank you.
I was wondering, I had a question on what do you think is the most challenging aspect for you in terms of whether it be like in the lab or just on your own independent project? What's been the most challenging for you?
So I would say the most challenging thing, in my opinion, is just kind of getting used to the reality that like most of the stuff you try isn't going to work. So as you've seen, like the things that are working, they're working, but not in the way we expected. So you kind of have to learn to roll with the punches a lot in grad school. So which can be really challenging at first. You kind of get used to it after a while, but it's kind of how science goes. You just got to, revise your approach as you get more information. And, it can definitely be, definitely demotivating at times, but, you just got to stick with it and, focus on the next thing.
I think that's just it's funny because that's a pretty common experience. I've had that experience. Most of my colleagues have had that experience, is that we're used to going through chemistry labs where 90% of what you do works. Then you go into a real life graduate situation where 90% of what you do doesn't work. And so it's like, wait, is it me? So it tends, like you said, it can be demotivating. But if you're expecting it and you're a little more tuned into it, I think that helps a little bit.
Did your advisor, I'll actually ask this question first. You said that all your colleagues have their own projects, but is it all in the same topic, even though it's a different project for everyone?
So there's a couple different subgroups in our lab. So there's CC activation. So there's a couple different kind of subfields even within that. So the cut and sew has been kind of a big thing in our group. So me and like 2 or 3 other people are doing that. There's also CC activation for unstrained, either unstrained rings or just acyclic bonds. So that's a couple other people are working on that, just through a different strategy. And then there's the aromatization-driven CC activation, which I kind of mentioned briefly as some background information. So there's also that. So those are kind of the 3 areas for our CC activation stuff. And then so there's also some CH activation, which is I don't have figures, so it's I don't have any schemes up here for it, so it's a little hard to explain otherwise. But so there's CH activation of like alpha and beta CH bonds on carbonyl compounds, and then CH activation on arrow groups, and then there's also this boron subgroup, which is to be honest, I'm not entirely sure what's going on in there because it is kind of new, and I don't go to the subgroup meetings for it. But there's some really like we did have paper published in a really high impact journal last year for basically just being able to insert a boron atom into a CO bond. So kind of things of that nature. As through nickel catalysis. And then there's some organic material stuff, though, with those being synthesized through, like a lot of, palladium catalyzed like CH activation reactions.
I find it interesting how you have your subgroup meetings. So even though like if you're not in their group, you can still like join their meetings.
Well, what do you mean?
You said that before, like it was like a short comment, but you said that you didn't attend like a certain meeting when they were going over a certain project of theirs. So are you able to like just hear what the other groups are doing?
I think if I really wanted to, I could attend, but nobody ever really goes to their subgroup outside of the one they're working in, just because they're kind of early in the morning, and frankly, nobody is really that enthusiastic about sitting through meetings. But we do have like full group meetings on Fridays where every like 3 or 4 months you'll present all your progress to the whole group from those last couple months. So that's kind of when you hear about things outside of your subgroup, but other than that, I would say it's really only the people doing CC activation who I know like what's going on more day to day with their progress or week to week with it.
When were you assigned to your groups, or did you pick which groups to be a part of?
So I chose. I chose the lab that I joined for Guangbin Dong, and then within that I chose CC activation as like a project to work on.
So your advisor gave you the option of picking what subgroup you wanted to work in?
Yeah, he for grad students, he's pretty open with doing whatever you want, I guess. Like that's why I can, pitch him like, hey, can I try this total synthesis? And he's like, sure. But for postdocs, he kind of hires them with an intention of like, you're going to work on this project and until it's done, and whether you like it or not, I guess. Which for some people it's if the project's going well, it's fine. But some people are, some projects are harder than others. So it's a little bit more of a struggle with that.
And I guess overall, I was wondering if you could like share your journey from like going to maybe like Harper, then to college, and then becoming like a grad student, like how that process was like.
Yeah. So I went to Harper for 2 years. Like I said before, like taking OChem with Professor Stanford was definitely, I would say, like a big turning point for my academic career. And he encouraged me to apply for a research program at Hope College, which is 10 weeks over the summer. So there I worked for a guy named Jeff Johnson, who also does CC activation, just with kind of some in a slightly different context though, or different I don't know, slightly different approach to it. And then I transferred to UIC after that, and then very shortly after I joined another lab doing some transition metal catalyzed like radical chemistry, and then so I worked there all throughout the school years, and then in my last summer there before my last year, and then I also went back to Hope to work for Jeff Johnson again for another summer before that, and then. Did
Jeff invite you to come back?
I I mean, I asked him, and he was on board with it too. So like, yeah, I mean, yeah, I
So
reached
you
out to
didn't
him
have to
about it.
go through the whole application process again?
I still had to apply, but he basically said like, just upload your application from last year and you'll be
It's a
accepted.
good,
Like,
it's guaranteed.
yeah, just like a formality, I guess. So yeah.
So that was still while you were an undergraduate.
Yeah, that was well, actually, so I did 2 years at Harper, then 3 years at UIC, kind of 2.5, just because I didn't the way they offer PChem there, and the prereqs for it, I just poor planning for my schedule. So in my I went back to Hope between my first and second year at UIC, and then worked at UIC between my second and third year there.
And then how about getting into grad school? What was that process like?
So definitely, I mean, it's stressful, but also like, I don't know, it's very foreign because like, especially once you start visiting places, because it's kind of like, I don't know, it's just weird kind of actually being there once it all, happens and you get accepted. But they do, once you get accepted, this is for chemistry. I can't say what it's like for every field, but for chemistry, generally, it also depends on the school too, but they'll pay for you to travel out to visit for a weekend. You'll, meet with faculty that you're interested in working with. And then, just get to meet grad students and just kind of mingle with people and see the city or area where the school is. And then, just hear more about the program and how things are run. Tour the facilities. But it was a little difficult too with my decision because it was like I visited like half the places I got accepted to, and then the pandemic started, and then all the other visits became virtual, which it's definitely harder to get a sense of like what the program is like there if you can't actually like visit in person, meet people, and see the area. Yeah.
So it's really about just like finding that right program and like advisor that you want.
Yeah, I mean, there's a lot of things to consider. Like, I mean, so I think probably at the forefront is like, what do you want to work on? Like, is someone there? Are you interested in what the people there are doing, and do you feel like their I guess management style and like personality, like they're people you could see yourself working for and are compatible with. And then facilities is another thing. That's something I really liked about UChicago is the facilities are really great here. For OChem, I feel like I have access to whatever I need for the type of research I do. So that's definitely a good selling point. And then I guess also like location, like, do you want to be in a big city versus like at, a big state school in the middle of nowhere? So preference in that too, or just at a small school somewhere else. And then also cost of living too is a big thing. So you do get paid. So at least this is just for chemistry. I can't say for every field, but for chemistry, they'll pay you to go to grad school and they'll cover your tuition. Like, you're not like making a ton of money or anything, but you're not incurring more debt, and you're not you can have a roof over your head and food and all that, and maybe a little bit of disposable income. So another thing that's really important is cost of living. So I looked at some schools out in California, but the cost of living is insanely high out there, and even with that, like UChicago pays me more than what, even though the cost of living is a lot lower here, UChicago still was paying more than what some of the schools in California were. So that was definitely a big factor in my decision too. And also my family's in Chicago, so like, just being near family too. So there's just a lot of things to consider. Ultimately, it's nobody can really tell you what the right school to go to is. It's really just a combination of different things, and what you feel is the best choice for you.
Thank you. I guess we have like a few minutes left, so I don't know if anyone else has any other questions or. All right. Well, thank you so much. I really enjoyed this. I was very scientific and I understood a little bit of it just from taking organic chemistry. But I was curious how that X-ray thing works.
So I don't really know. So I mean, we have an X-ray diffractometer in the basement of our lab building. So there's a guy who runs it. He maintains it, runs people's samples. But so your lab has to pay to use stuff like NMR and mass spec and things like that, and X-ray diffraction. And the X-ray diffraction experiments, I don't know I don't remember the exact cost, but it's pretty expensive. Like if the guy who runs the facility runs it for us, it's like $1,000 per sample or something crazy. But so we have, so our group's like 20 people. So at any given time, we'll have like 2 people assigned to who are like trained on how to use the X-ray diffractometer. They'll prepare samples and run them and do all the data analysis. And it is like at least half, if not half the cost, if not cheaper. But as far as how it works, so it's like, so you have to grow crystals of your compounds. So that's probably the hardest part, is actually getting a good crystal for it. And that immediately limits you to only being able to analyze things that are solids. So basically, if you grow a good enough crystal, it can act as like a diffraction grade, or the molecules and atoms can act as a diffraction grating. And X-rays are very high energy, so it can be diffracted by them. So again, I don't know all the details on how it works, but just the kind of general workflow of it is the crystal, the atoms in the molecule diffract the X-rays, and that generates a pattern. And then through some computational stuff or data analysis stuff that is way above my pay grade, you can basically kind of like I don't know if reverse engineer is the word, but kind of.
That's not a bad description. It's kind of like a Fourier transform, and then you separate it out into, and this pattern kind of leads you to saying there's these structures.
Yeah, so you can tell where things are. So not only can you get like it's like this where was that? So you get something like this. There's also special software for it too. This is just a PDF thing it gives you, but if you have software for it, you can get a lot more in-depth looks at it, including like rotating it and everything. But so this is, oh, sorry, go ahead.
Oh, I just said, yeah, it looked like you could rotate around it instead of just like you were given like a 2D structure.
Yeah, so this gives you like not only the structure, but also like you can get, depending on the quality of your data, you can get like exact bond lengths and stuff like that. And this is also really helpful too, especially for like asymmetric catalysis, because if you have something that's just one, like a single enantiomer, you can use this to tell where things are in space, which tells you which like the exact configuration of it. So this is like the gold standard for structure determination, but it's also like, because of the difficulty of getting good crystals, it's also like the I guess hardest to use, or least user friendly, I would say.
Well, thank you. I guess that's it then. It's 4 o'clock, or no, 5. My bad. It's 5. But thank you so much. I really enjoyed this, and
thanks for inviting me.
Yeah, of course.
And if any of you have any other questions about grad school or anything, like feel free to email me. I'd be happy to answer.
Yeah, I can send your email out. Yeah. All right. I'll see everyone next week.
Good job, Cole.
Thank you very much.